We still in the section static range minimum queries, and in the previous part of the section we solved the problem using a dynamic programming approach. As a result, we get a runtime error because we exceeded the memory limit of the task. As you see in the picture here, the memory limit of the task is 512 megabytes, and by using the dynamic programming approach, we have here a space complexity big O n squared that gives me a 152,578 megabytes by using integer here, a matrix of integers, which is, as you see, is a very huge amount of memory. In this part, we will try to fix this issue by using a different technique. There are several approaches that we can use, like square root decomposition, sparse table, lowest common ancestor, and segment tree. We have used the naive approach, dynamic programming, we have used it. In this section, we're going to use this square root decomposition. As you see here, the space complexity is O square root of n, where n is the size of the original array. The time complexity, we have to build an array in big O n, and one query costs big O square root of n. The principle or the goal of using this approach is to reduce the space allocation used in dynamic programming method. The main idea or the principle of the square root decomposition is to divide the array, the original array of size n, into different blocks of size square root of n each. And then we compute the minimum of every block and store the result. If I have n is the size of the original array, so we have to compute m, which is square root of n. The ceiling of square root of n is the size of the blocks array. So we have to divide the original array into m blocks, and we apply the function f on those m cells and store it in the blocks array. For example, here the first m cells, their result is stored on the first cell in the array blocks, and the second or the next m cells, the result f of these m cells, their result is stored on the second cell of the array blocks, and so on until the last m cells or the remaining cells are stored on the last cell. So here, as you see, we have the blocks array of size m from 0 to m minus 1, where m is square root of n, the ceiling of square root of n, and a is the original array. If I want to know if what is the range or the minimum between two boundaries from left to right, this boundary, or the sum or the max or the any other function. So we want to apply here f on the original array from left to right, as we have seen in the first parts of this lectures. Of this lecture, f it could be min or max or sum or JCD or product or any other function. So here we can use, as you see here, this block lies to the range. So this red block lies to this range. So we can use it entirely, this block. We can use this result in the array of blocks. For the remaining cell, we have to compute it and then compute the remaining cells. Let's take an example here, or before that, let's see how to build this array blocks. Here I have an array of size 8, so m will be the ceiling of square root 8 is equal to 3. So I have to divide the original array into blocks of the 3 cells each one. And for the first 3 cells here, I store their minimum into cell 0 or in index 0 in the array blocks, which is -1. The next 3 cells, 2, -10, 2, their minimum is -10, is stored in the index 1 of the array blocks. And the remaining cells here, this plus 2 cells, their result, their minimum is stored in the last cell of the array blocks. So we have here an array blocks that store the minimum of each 3 cells in the original array. The pseudocode of this function, if f is minimum, how to build this array. This function takes as parameters the original array, the size n of the original array, and the size m computed. The size m is computed, which is the size of the array blocks. And we have to iterate. Let's take an example here. And we have to iterate from 0 to n minus 1 and compute for each block the minimum of the 3 or the m cells on the original array. Let's take this example. If I start from index 0, I is 0, this formula gives me the index or the index of the array blocks. In which block, I will store the minimum. For I equal to 0, so I will store the minimum in the block 0 over 3, which is the number of cells on each block from the original array, which is m, equal to 0. So we have to compute this 3 cells here. The result must be here. Let's see together. So blocks of 0 is equal to the minimum plus infinity. I initialize array blocks by plus infinity to start computing the minimum, which is 5. Minimum plus infinity and 5, which is 5. This 5 will be stored in blocks 0. And I goes to 1. Now 1 over 3 is still 0. So the result will be stored in blocks 0. Blocks of 0. Now blocks of 0 is the minimum of the computed result in the block 0 and minus 1, which is in the original array. which is equal minus 1. So blocks of 0 will be minus 1. And I goes to 2. 2 over 3 is 0. Blocks of 0 is the minimum between the previous computation on the array and on the cells on the cell block of 0, which is minus 1, and the new common one from the original array, which is 7. So here the minimum is still minus 1. I now goes to 3. So we have to store all the 3 elements in this block. So 3 over 3 is 1. So blocks of 1 is the minimum of the previous computation on the array blocks in index 1, which is plus infinity, initialized by plus infinity, and the new common value from the original array, which is a over 3, which is 2 here. So the minimum between plus infinity and 2 is 2. So blocks of 1 is 2. I goes to 4. 4 over 3 is 1. So in blocks of 1, we will store the minimum between the previous computation and the blocks of 1, and the new common value from the original array, which is A4, which is minus 10 here. So the minimum between 2 and minus 10 is equal to minus 10. So blocks of 1 will be minus 10. 5, I goes to 5. 5 over 3 is 1. So blocks of 1 is a minimum of minus 10. Previous computation on that previous result on the array block of 1, and the new value from the original array in A5, which is 2. The minimum is the minus 10. Okay, here the minimum will be still minus 10. Now, these two will be 6. 6 over 3 is 2. So blocks of 2 is the minimum of the previous computation in the array blocks, or on the cell blocks of 2, which is plus infinity, and the new value from the original array, and common value from the original array, which is A6, which is 0 here. So the minimum will be 0. And the final value in the original array, A7. So I is equal to 7. 7 over 3 is 2. So blocks of 2 is the minimum between the previous computation from in the cell blocks of 2 and A7, which is 15. The minimum will remain 0. As you see, this is the pseudocode how to fill this array. Its type complexity is big O of n, as you see, and time and space complexity is O is square root of n. Let's see. Okay. How to perform a range query? Let's see let's say general example here, but I will take values here to understand what's going on. So as we have seen, the original array will divide it into blocks, and now we want to compute the range query from 0 to 9. It could be the sum, the minimum, the max. I don't care here of the function. Any function will go here. So we put the pointer and the left boundary. So f of a between 0 to 9 will be what? We compute by putting the pointer at index 0, because here the left boundary is 0. And we have to ask two questions. Are we in the beginning of a block, and can we use that entire block? And in this case here, we are at the beginning of the block, the green one here, as you see, the green block. Can we use it, all this block? The answer is yes too, because the right boundary is 9. And if I add 0, I add the number of cells that make a block, which is 4 here in this case. 0 plus 4 is 4. So we do not reach 9, the right boundary. So we can use all the entire blocks of 0 in the computation as in the result. So f from 0 to 9 in the original array is equal to f of blocks 0. We can use that block. And we jump to the next. This block is used, so we jump over this block, so which means we add the 4 to 0 if m is equal to 4. We are at position 4. We ask again, can we use this block? Or before that, are we at the beginning of a block? The answer is yes. Can we use this entire block? The answer is yes too, because 4 plus 4 is less than 9. So we can use this red block in the result, in the computation blocks of 1. As you see here, instead of running over all the cells here, we just use this block. So we jump that block, we come to A. Are we at the beginning of the block? The answer is yes. But can we use the entire block, the yellow one here, all the cells? The answer is no, because we want only these 2 cells in that block. So we don't use the entire block. We use a part of that block. So we have to take these cells one by one, which means we take AA and we add 1 now to pointer. We come to 9. Same here. We are not at the beginning of a block. We will not use the entire block. So we only use that value at A9. So as you see here, this is the final result. Of course, here we stop because we exceed the the right boundary. As a result here, f of in the original array from A to 9 is f of this block, this result, and this result, and this 2. Let's take another example here to understand more what's going on. Of course, as usual, we'll divide the entire original array into blocks, and you want to compute, for example, from range to 2 to A. We point the pointer at index 2 on the left boundary, and we ask a question: are we at the beginning of a block? The answer is no. So we will not use that block. So which means we only will want to use A2. This value, only this value. And we add 1 to the pointer, it comes to 3. We are not at the beginning of the block, so we will use only that value on the result computation, A3. We add 1 to the pointer, we come to 4. 4 is the beginning of a block. And can we use the entire red block here? The answer is yes, because 4 plus 4, which I took 4 here, the size of the block, is equal to 8. So we can use this block in the result. and we jump over that block. We come to 8. 8 is the beginning of the yellow block, but we will not use the entire block because we stop there. We will use only the value at the position 8 on the original array. So we take it A8. The pseudocode of this function, it will take as parameters the original array, the array blocks, the size of the blocks, the left boundary and the right boundary. Of course, we initialize the answer to plus infinity if f is min, minus infinity if f is max, 0 if x is the sum, 1 if f is the a product, and so on. And while the left boundary still less or equal to the right boundary, we ask the question, are we at the beginning of a block? And can we use the entire block? If the answer of both these questions is yes, so use that block. And the answer here, you will use the block and we jump over that block by adding m to the left boundary, as you see. Else, which means we cannot use the entire block. So we will use the elements in the original array one by one. Use the current value in the input array. Okay. Let's code the solution of the problem. I think the problem is here at the beginning. I will change the name here because I will make a new file. Static image minimum queries. Now let's remind together with the problem statement. Given an array of an integer, the task is to process Q queries of the form what's the minimum of the value range AB. So at the first we are given the size of the array, of the original array, the number of queries, the value at that array, and we have to find the minimum between in range AB. Okay. Look, I will code it from scratch. First, I will read the size of the array n and the number of requests q. Then we will fill the original array by the given values. We fill the original array by the values given in the problem here. Okay. Okay. Now we go and compute M, the size of the array blocks. Let's make a function that fill or build the array blocks. I call it B here. We will take as parameter original array A, the size of the original array, and the size of the array of blocks. Let's make it here. Build. So we'll take as parameter the original array, the size of that original array, and the size M of the array blocks. We will iterate over the original array. And as we have seen in the pseudo code, compute for each M cells, compute the minimum, their minimum in that specific block, which is the minimum between the previous computation in the array blocks and the new incoming value from the original array. Okay, here I will first declare the array blocks. And here we have to return that array. Okay. Let's implement the function range query. It will take as parameter the original array, the array blocks, the size of the array blocks, and the left boundary and the right boundary. Okay. Let's initialize the answer to plus infinity. Okay. In C++, I will use the numeric limits. Sorry for this. In C++, I'll use numeric limits plus infinity, which is max here, the function max, and the numeric limits namespace. And we keep checking if the left boundary is always less or equal to the right boundary. If yes, we will say check if we can use, if we are at the beginning of the block, which means the middle of the left boundary by M is equal to 0, and check if we can use that block to the left by the pointer left boundary plus m is less or equal to. If the answer is yes, so use that block in the answer. So it will be the minimum between the old answer and that block. L divided by m. And jump. Go to the next block or jump that block. Blocks here. Sorry, B. Okay. Else, if we are not on the beginning of the block, or we cannot use that block entirely, so use the element of the original array only. Use only the element of the original array. How do you say that? So the answer is equal to the minimum between the old answer and the incoming value from the original array. 8 plus plus, we add 1 to jump to the next value on the original array. And here, of course, they have to return that answer. So now we iterate over the queries. Iterate over the queries. Read the left boundary. Read the left boundary and the right boundary. Read left and right. Now we will compute. We will display and compute and display the minimum, the range minimum dash query from left to right using the square root decomposition technique. You have to reduce 1 here because in the problem the left and right boundary are 1 based index. Okay, too few arguments. We still have one here. I think m, yes, the size of the array blocks. Okay. Okay, let's see what happened now. I think all is done. Let's see if there are some mistakes. Yes. I expected the 211, 2104. What's the problem here? Let's check the build array. Okay, the problem here is I think I didn't initialize the array blocks to plus infinity. So here I have to initialize all the array to plus infinity. To get the correct result. So here I have to take this, it's better to take this one. Let's make constant, let's call it infinity, INF, infinity, define infinity to this. Is equal to infinity. is equal to infinity here. This one blocks. Okay, this test is passed. Let's try to submit it. This, static management queries, this one. Okay, as you see, all tests are accepted. Using the technique, square root decomposition technique, the test is passed, as you see. What about the memory here? The memory is the space complexity of this code. The space complexity is O(n) for the blocks array, O square root n, O big O square root n for the blocks array, and O(n) for the original array. So in total we have, if we have n is equal to 200,000, so we have the space complexity 200,000 plus the ceiling of the square root 200,000 multiplied by 8, which is the size of long here in C++. So we get 1.5, let's say 1.6 megabyte, which more or less less than the memory limit here in the task. As practice now, I suggest for you to repeat the problems static range sum queries and range XR queries using this technique, the square root decomposition technique.